In chapter 6.3, we're going to start talking about something called a binomial distribution, as well as a geometric setting as well, which is pretty similar. And let's take a look back at this example we started with. We said, I've got this coin, I'm going to flip a coin 4 times. And we said that if I get more heads, so 3 or more heads, I win. If we get an equal number of heads or less, you win. So we were able to calculate the probability by mapping out the entire sample space. We looked at all the possible things that could happen if we flipped the coins 4 times. Turns out there are 16 different outcomes. And then we were able to look at this and say, okay, probability of 4 tails in a row is just 1 out of 16 because there's one outcome where it's all tails out of the total 16. And we were able to do that because each one of these outcomes are equally likely. And that's because the coin flips are independent and the probability of heads and tails was the same, or so we thought. We later found out that I was cheating and that actually the probability of heads was not 50%, it was more like 0.72. Okay, so I was cheating, I was trying to get heads and I was working on my flip with this big coin, trying as hard as I could to get a heads every time. And so if that's the case, if the probability of heads and tails are not the same, then getting 4 heads and 4 tails is not equally likely. So we can no longer use just this simple sample space to calculate our probabilities straight away. Instead, we need to think about this probability a little bit harder. So let's say I want to know what's the probability of getting 3 heads. Okay, so the probability of getting 3 heads I don't like the way I'm writing this out. I'm going to fix this with some notation here. So I'm going to use a random variable. I'm going to say, okay, x is my random variable, and this is going to stand for the number of heads that I flip, okay, out of the 4. Okay, so I'm going to look for what's the probability that big X, which is the number of heads I get, is equal to 3. Okay, so we can still do this, even though the probability of heads is 0.72, which means the probability of tails would be, not that, 0.28, 1 minus 0.72. So okay, I would look at this and say, what I want to happen is I want to get 3 heads in a row followed by a tails. All right, 0.72, 0.72. We can simply multiply these together because these are independent events. Whatever happens in the first flip doesn't affect the second flip. So we can just multiply those probabilities together. So heads times heads times heads times tails is what we're looking for. But that only covers this outcome. Okay, we can see there's 3 other ways to get 3 heads and a tails. So I need to take whatever this value is and multiply it times 4 because there's 4 different combinations of 3 heads and a tails. So I can do that. We've got 0.72 and we're going to raise that to the 3rd power because I've got 3 of them, right? Times, oops, don't want that in there, times 0.28, and then we're going to multiply the whole thing by 4. So under this new probability, if I'm getting a heads 72% of the time, the probability that I get 3, x equals 3, is 0.418. Okay, so if we're still trying to look for what's the probability that I'm going to win the game, we could do the same thing for what's the probability that x is going to be 4. In other words, what's the probability that all 4 flips will be heads? This is a much simpler problem because there's only one way to do this. Right? There's only one way to get 4 heads. There's only one combination. So we just do 0.72 to the 4th power. Okay, so there's about a 27% chance that that would happen. Okay, so it looks like that if I can flip this coin on heads 72% of the time, which from the from the 6.1 video looks like I could, then this plus this is greater than 50%. I'm going to win the game more than you're going to win the game if I'm able to skew the odds in my favor. Okay, so this is a fine way to do this, but it's pretty limited. We can see right here because we drew out the entire sample space, we can see pretty clearly, and I'm going to go ahead and get rid of this guy, we can see pretty quickly that there are 4 different ways to get 3 heads out of tails. But let's say I wanted to flip the coin 15 times. I'm going to flip the coin 15 different times. What's the probability of me getting 10 out of 15 heads? It's kind of the same question, 75% heads, but it gets much more complicated to solve. How many different ways are there to combine 15 outcomes where 10 of them are heads? There's a lot. And that gets really complicated really quickly. So we need a new method. We need a more efficient way to solve these types of problems. Enter the binomial setting. So what we're looking at is an example of a binomial problem. So that's what 6.3 is all about, binomial and geometric distributions. And we'll get to geometric later, but I want to really focus on binomial for today, because that's what we're doing right here when we do this probability calculation right here. Okay, so if I want to know if I'm presented with a probability problem, and I want to know, can I apply binomial calculations to this? I have a quick way to check and see if this is binomial. I check the bins. Okay, so this is going to be our little mnemonic device to help us check and see if a binomial setting is appropriate. So the first thing we check for is binary. So binary just means that there are 2 possible outcomes. In this case, it's very simple to see that we have 2 possible outcomes, heads or tails, but this actually can be expanded to lots of things. We just have to say that there's probability of success and probability of failure. We could easily define any kind of event as success or failure. For example, let's say I had a big bag of M&Ms. In this M&M bag, there are 6 different colors of M&Ms. So you might think this can't be binary because we have 6 different possible outcomes. But depending on how we define our random variable, right? For example, we said x equals number of heads. If I said, okay, my random variable m is the number of blue M&Ms that I pull out of the bag, that's not blue, number of blue M&Ms I pull out of the bag, then we have a binary situation. The M&M is either blue or it's not. Okay, so it's easy to define things so it's set up as a success or a failure. So 2 possible outcomes. The next requirement is independence. So when I flip the coin, we have independent events. Right? It doesn't matter what happens on the first flip. It doesn't affect, knowing what happened on the first flip doesn't affect what happened on the second flip. The next thing we need to know is the number of trials we're going to go through. In this example, we're flipping the coin 4 times. Okay, so we know the number of trials in advance. And this is where things get a little bit different in the geometric setting, but we'll get to that in a minute. So we know how many trials we're going to do. Right? We want to approach the problem by saying, what's the probability of 3 heads out of 4, right, if I flip it 4 times? Finally, we need the same chance of success on every single trial. So we're going to assume that every time I flip, I have about an equal chance of getting a heads. So same chance of success every time I flip the coin. Geometric settings are a little bit different. So another example that gets a little bit away from our coin flip. Let's say I wanted to draw some M&Ms out of this bag. And we can set this up as either a binomial setting or a geometric setting. So first, let's do a binomial setting. So in a binomial setting, I need to be interested in a single color. That way we can define this as success or failure. So here I'm interested in what's the probability that I draw out a blue M&M. So what I'm going to do is I'm going to draw out 10 M&Ms every time I do my sample. Okay, so I'm going to draw exactly 10 M&Ms. Then I'm going to count how many of those M&Ms are blue. And I'm seated in a way that I can't see into the bag, so I am just drawing the M&Ms at random. That time I got 4 blue out of 10, and I'm going to put those M&Ms back in the bag and reshuffle, and then repeat the process. So this would be a binomial setting. I know how many M&Ms I'm grabbing, so my number of trials is set, 10 M&Ms every time. It's a binary situation because it's either blue or it's not blue. We don't care what color it is if it's not blue, just success or failure. And we have rough independence. Ideally, I would put all these M&Ms back and reshuffle every time, but there's hundreds of M&Ms in this bag, or at least there were. So we have roughly the same chance of success and independence on every trial. A geometric distribution would be a little bit different. So instead of saying I'm going to draw 10 M&Ms out of the bag and then count the number of blues, for a geometric distribution, I don't know how many trials I'm going to do. I'm going to draw an M&M and look at it. If it's blue, I stop. If it's not blue, I'm going to put it back, and I'm going to draw another one. Now I've gotten a blue, so I'm going to stop. So in a geometric distribution, our sample size is not set. We continue the process until we get success. So we could get a blue on the first trial, or it could take 10, right? We don't really know. So here I'm doing a geometric setting. I'm going to draw M&Ms until I get a blue one, and then record how many trials it took to get blue M&M. So I'm going to put it all back and reshuffle. So we have a binary situation. It's either blue or not. We have independence mostly. Ideally, I'd put each M&M back and reshuffle, but there's hundreds of M&Ms in this bag, so that probability difference is going to be really, really small. The number of trials we don't know. It's until success. And finally, we have roughly the same chance of success every time we draw an M&M out of the bag. But the M&Ms have been compromised. So let's go back to our coin flip example. Okay, so we were able to calculate what's the probability of getting 3 heads out of 4 pretty easily. But that's because we were able to map out the sample space and do a quick count of how many different ways are there to get 3 out of 4 heads. If we were doing 15 trials, that would be much harder to do. So luckily, we do have a formula. Unluckily, the formula is pretty ugly. So if you look at your formula on the AP Statistics formula chart, you'll see this box down here with the probability distribution section. It says if x, the random variable x, has a binomial distribution with parameters n, that's the number of trials we're going to do, and p, that's the probability of success, then this formula will solve it. So we've got p, so the probability, go back to black here, probability that x, number of heads, is equal to x some value, so this is big X and little x, those are different, is equal to n choose k of the probability of success to the x power times the complement to the probability of success, aka the probability of failure, to the x or n minus x power. Okay, so this is a really complex formula. There's a whole new branch of mathematics that's been thrown at us in this formula. You might be wondering, what the heck does that mean? N over k, but without the fraction? What is that? N choose k. N choose k is some combinatorics. So this is the mathematics of counting things. And n choose k is basically saying, if we have n number of trials, how many different ways are there to combine k successes? In other words, if I say I'm going to flip the coin 4 times, how many different ways are there to get 3 heads? So there's a way to calculate this. We take n factorial divided by k factorial times n minus k factorial. You might be wondering, what's an exclamation point mean? So let's look at an example. Let's say I wanted to do, all right, I'm going to flip the coin 4 times, and I'm wondering how many different ways are there to get heads. So we already know the answer. We found out there's 4 different ways to get 3 heads out of 4. So let's see if we can do this with the math. So if you've never seen a factorial before, I'll show you what that means in just a second. And again, n is the number of trials, 3 is the number of successes that we're looking for. So 4 factorial means 4 times 3 times 2 times 1. We multiply all the way down. 3 factorial would be 3 times 2 times 1, and then 1 factorial, well, that would just be 1. 1 times nothing. So we get 4 times 3 times 2 is 24, over 6 is 4. So mathematically, without drawing anything, we can calculate the different number of ways we can do this. So again, factorial means we're going to multiply times each integer below that number. And this is fine to do by hand, but as usual, we have technology. There is a better way to do this. So first, let's look at how do we do this part. How do we do the binomial coefficient? That's what this is called. How do we find this factorial thing? Well, in your calculator, there's a way to do this. If you go to math and over to probability, we have this right here is a combination. So we can do n, choose 3, and we get 4. This is great because even with this formula, it can get kind of ugly to do. If we had, for example, 15 choose 10, again, we could use this formula to calculate, or we can just throw it into the calculator. So we can say, okay, 15 probability, choose 15, choose 10. There are over 3,000 different ways to get 10 heads out of 15. You're probably surprised about how big that number is. I was. These things scale up really, really quickly. So knowing how to use your calculator is really, really important. But if you know what you're doing with binomial distributions, we don't really need to even do any of this. We can take our entire probability problem and throw that thing into the calculator. So as long as I can identify all the different pieces of what I need, I don't really need to sweat this formula too much. But it's really not as complicated as it might look. We've actually already done it over here. All right, we've got, what's the probability that number of heads will be equal to 3? Well, we found out how many different ways we could get combinations of 3 heads out of 4. We figured out there were 4 of those. Okay, we then took the probability of success, 0.72, and raised it to the x power, the third power. So you can see we do 0.72 to the third power right here. We did it in a weird way. We multiplied 3 times. It's the same thing. Then we looked at the complement of that, so 0.28. We raised that to the first power, 4 minus 3, the first power. So we've actually already kind of discovered this formula. But let's say we wanted to do something more complicated. So let's say we want to figure out what's the number of heads I could get. So that's our random variable. But let's say instead of doing 4 flips, I'm going to flip this coin 15 times. And I'm interested to know what's the probability that I get 10 out of 15. So let's plug it into our formula. And again, we said the probability of heads when I flip this coin is 0.72. That's our estimate, at least. Okay, so the probability that number of heads is going to be equal to 10. We're looking for what's the probability that I can flip this coin 15 times and get 10 heads exactly. Well, we'd first say, okay, out of 15 trials, how many different ways are there to get 10? We take the probability of heads, which we found was 0.72, using my cheating method. We're going to raise that to the x power, so to the 10th power, because we want 10 heads. And then we're going to multiply by the complement, 0.72, this will be 0.28, times how many failures we want, so 5, right, n minus x. So we could throw all this into the calculator. We could, again, do this factorial garbage to figure out the binomial coefficient is 3003, or better yet, I can throw this whole thing into my calculator. So, important part here, we need to know how to do a binomial distribution in the calculator. So if I go up to the distributions button again, this is where we find normal CDF. We're going to scroll down until we see binomial distributions. So right here I have binomial PDF. PDF stands for a precise value, and I want exactly 10 heads. So I'm going to do binomial PDF, and P because I want one precise value. We'll look at CDF in a second. Okay, the number of trials we're doing 15 coin flips. My probability of success is 0.72. Notice that your p-value is always probability of success, okay, not failure. And then my x value, I want to know what's the probability of getting exactly 10 heads. And we're going to throw that whole thing into the calculator and figure it out. Okay, so if I flip this coin 10 times, the probability of getting exactly 10 heads is about 19%. So your calculator is super useful for a problem like this. It can calculate probabilities really quickly if you know how to use it. What if I wanted to know what's the probability of, for example, you winning this game? So I said, okay, if I get more heads than tails, then I win. Get less, same number of heads or less, then you win. So for 15 trials, you would win if we got 7 or less heads. So we can solve this just as easily with our calculator. All right, and often these types of problems are really useful. You can also imagine that if I wanted to know, well, we'll get to that in a second. So we're going to do something really similar here. We're going to go to Binomial Distributions. So again, the distribution button. Go down to Binomial Cdf. So Cdf is a cumulative distribution function. So that's going to take the number that we're looking at, 7, and then look below that as well. We've used CDF before. Remember, we used normal CDF. We looked at a value here and we said, okay, what's the probability of anything below that value? That's what CDF means, the cumulative value. So up to that point, what's the probability? So same thing, different distribution. We're looking at a binomial distribution now, which looks slightly different, but same idea of what's the probability of this value or below. Okay, so CDF can help us answer this question. So we're going to fill this out again. I'm doing 15 coin flips. Probability of getting a heads is 0.72. I want to know what's the chance of 7 or less heads. Oops. And we're going to get, so again, in number of trials 15, probability of success was 0.72, and we wanted 7 or less. So x is less than or equal to 7. We get a chance of 0.034. All right, so the more I flip this coin, the more likely you are going to lose, because I'm better at getting heads, so the more we flip, the more likely I am to get a majority of heads. You might be asking, well, what if we wanted to know what's the probability of x being greater than some value? Well, there's no direct way to do that in your calculator, but you could see pretty easily that if I want to know what's the probability of x being bigger than 7, well, I can just do 1 minus the probability x is less than or equal to 7, right? We've done this before with normal distributions. If I want to know what's the probability of above some value, I just do 1 minus probability below that value. Okay, so that's the big idea. This section is pretty difficult. This feels like a lot of new stuff thrown at you at once. We've got a whole new branch of mathematics, combinatorics, but really, if you know what you're doing with the calculator, you'll never have to do any of this by hand. And that doesn't mean you should never learn it. You should take some time to look at the formula, think about these processes, read the chapter, and try to understand as much as you can about this process, because it'll help your understanding if you're ever asked about what you're doing and not just expected to solve the problem. But again, the calculator can take us really far in this section. We're going to be looking at a lot more examples next week during class. We'll look at some examples of where we can use binomial distributions and geometric distributions to solve all kinds of problems. So this video is just to get you prepared, to get you introduced to the idea. We're going to start the 6.3 homework later, so your only obligation for today just to watch this video and get prepared to jump in to 6.3 next week. Yeah. All right, guys. So watch the video, rewatch sections of the video if you need to. Some of this stuff is a little bit confusing. You might need to rewatch. Definitely want to read the chapter. There's a tough one. Have a great weekend. Enjoy the weather, guys. I'll see you all next week.